Welcome back. In the last video, we showed that spans and subspaces are actually the same thing. In this video, we'll see how we could apply that knowledge to examples. So let's start. Proposition 7.5.1 gives some insight on subspaces. We know that subspaces are, well, they're spans, and so we know spans. It could be 0. It could be one line containing or through 0. Next biggest thing is a plane through 0 and so on. And so we have an idea of what they look like geometrically. In the next example, we can use that insight to determine whether a given subspace is a subset is a subspace. So example 7.5.3. Determine whether S, which is the set of all vectors in R2 xy, so that x times y is 0, is a subspace of R2. If it is, prove all three properties. If it is not, find a specific counterexample for one of the three properties. So this is a case where you have first to decide whether it is a subspace or not. And it's not always easy. So let's see if we can't use our newfound knowledge. So this is what we're looking at. X times y is 0. So that's the same thing as either x is equal to 0 or y is 0 or both. And if I sketch this, I have two different sets. This is y is 0, this is x is 0, and so I'm getting kind of two intersecting lines. So because I have two lines, it's not one of those. So I would say it's not a subspace. And now I can try to figure out why it isn't. So let's look at these two lines. It contains 0. I have 0 here. If I take a vector and I stretch it, I'm still going to get a vector. So that third property would work. So it has to be the second property. Has to be the second property. So what I'll do is I know the fact that I have two lines is going to make me fail. So I'm going to take a vector on each line. And then if I add it, I'm going to get something that's not in the green. That's perfect. All right, so let's see. I'm going to take V, which is 1, 0. That's in S, as x times y is 1 times 0 is 0. I'm going to take W to be 0, 1. Again, that's in S, as x times y is 0 times 1 is 0. So I have two elements that are in S, and then if I take the sum will be 1, 1, which isn't in S, as if I take x times y, I get 1 times 1, I get 1, which is not 0. And so property 2 fails, and S is not a subspace. All right, so my insight on what subspaces look like helped me determine that it wasn't a subspace, but also kind of sent me on a path to figuring out why it wasn't. Okay, so note that using our knowledge of spans, we can now show that a subset of Rn is a subspace without proving all three properties. All right, so we can skip all that work if we can just show it's a span. In future examples, however, we may force you to show the three properties. So if an example is phrased this way, then you are forced to prove the three properties, but if we don't mandate it, you can definitely skip it, as I'll do in the next example. So example 7.5.4, consider the set V of vectors in R4, so that 2x minus y plus z is 0, and w equals x plus y plus z. Show that V is a subspace of R4, find a basis for it, and give a geometric description of V. Right? So I could prove the three properties, but let's instead show that it's a span. So I'm going to need to solve this. So V is a solution set of, is the solution set, sorry, not a, of, all right, so I have w minus x minus y minus z is 0, and I have 2x minus y plus z is 0. I'm going to solve this system. So if I solve it, I'm going to get 1, 0, 0, 1, minus 3 halves, 3 halves. I did this ahead of time, and 1 half. So I have two leading ones. I have two free variable. That's going to give me two parameters. And so I'm going to get, first was W. So W is 3 half S minus 3 half T. Then it's X. X is 1 half S minus 1 half T. Y is S. Z is T. So what I get is that W, X, Y, Z is vector times S plus a vector times T for S and T in R. So I get 3 halves, 1 half, 1, 0, minus 3 halves, minus 1 half, 0, 1. And so what I get is that V is the span of these two vectors, which means that V is a subspace. It's a span, it's a subspace. And then, so if you solve the system and get that V is a span of some sort, or if you've managed to write your set as a span, you don't actually have to show the three properties. We've done it in general. All right, so we've done the first part. I need to find a basis for it. Well, I have my candidates here. So let's put that one, A, sorry, and then B basis. I'm going to start with this, and I'm going to reduce it. Something's really nice about these vectors. These two rows are so clean that it's going to be super easy to reduce it. I don't even need to use a computer algebra. I'm going to bring these to the top, and then I'll be able to get rid of everything else. And so my basis is going to be exactly those two vectors. They're linearly independent. Remember, you keep the ones corresponding to leading ones. So this is your basis. All right, I have two elements. That means give a geometric description of V. That's going to be part C. V is a plane because it has dimension 2 in R4 containing the origin. That's it. All right, so in the next example, we'll prove one more proposition that's going to build on this example, actually. And then we'll be done.